Hello everyone, welcome back to my YouTube channel. So today I'm here to present about the topic, the pigeonhole principle, a simple idea with powerful implications. So let us begin with the topic, what is pigeonhole principle? So let us discuss about the statement and simplified concept and surprisingly useful things. So if n items are put into m containers with n is greater than m, then at least one container must contain more than one item. This ensures that when the number of objects exceeds the number of categories, some category must have a surplus. So let's discuss about the concept. Imagine you have more pigeons than pigeonhole available. So when each pigeon files into a hole, at least one hole will inevitably and end up with two or more pigeons. It's seemingly a trivial truth that underpins many complex proofs. So in what all fields are this pigeonhole principle useful? So despite its simplicity, this principle is an incredibly versatile tool in various mathematical and computational proofs. It allows us to reduce existence without having to construct or identify the specific instance, which is invaluable in many scenarios. So let us take a basic example called stocks. So in stocks, you have the problem. Let us discuss about the problem, applying the principle, and how we conclude the solution. So the problem, you have a drawer containing 10 black socks and 12 blue socks. The challenge is to determine the minimum number of socks you must pick from the drawer to guarantee that you have at least one matching pair of the same color. So when we apply the pigeonhole principle, which is m greater than n, here our pigeonholes are the two possible colors of socks, black and blue. Consider black as m and blue as n. So the pigeons are the individual socks you pick. To guarantee a pair, you need to pick more socks than there are colors. So the solution is, for this principle, if you just pick two socks, you might pick up one black and one blue. However, if you pick up the third socks, it might be either black or blue, thus creating a matching pair with one of the first two socks. So picking 3 socks guarantees a pair, since 3 is greater than 2. Next, let us move to another example called birthdays. Here, to depict this concept of pigeonhole principle, we are taking birthday as an example. So the claim, consider any group of 13 people. It is mathematically certainly that at least two of these individuals must share the same birthday month. This is classical illustration of pigeonhole principle. Identifying elements. In this scenario, the pigeonholes are 12 months of the year, January through December. The pigeons are 13 people in the group. So the proof, since we have 13 people, pigeons, and only 12 possible birthday months, which is pigeonholes, and 13 is greater than 12, the pigeonhole principle states that at least 2 people must share a birthday month. A further generalization states that in any group of n plus 1 people, at least 2 share a birthday. So this example, it clearly depicts the pigeonhole principle. Next, we have generalized pigeonhole principle. Let us understand more detail about this pigeonhole principle. Like considering all these examples, we conclude the principle as the generalized pigeonhole principle states that if n items are placed into m containers, then at least one container must contain at least n/m items. This is a powerful extension which allows for more understanding of the distribution. Understanding the ceiling function. The symbol x represents the ceiling function. It means the smallest integer that is greater than or equal to x. For example, 3,14 is equals to 4 and 5 is equals to 5. This function ensures we always round up to next whole number. Uneven distributions. So when the basic principle guarantees at least one hole with more than one pigeonhole, the generalized version provides a minimum number of items in the most populated container. This is crucial for analyzing situations where items might be distributed unevenly. So next we have, next to depict the pigeonhole principle, we take exam scores as an example. So in this, the problem statement will be like this. If 101 students take an exam graded on a scale from 0 to 100, at least 2 students will inevitably receive the same score. This scenario beautifully demonstrates the power of pigeonhole principle in predicting the outcomes. Next, if we consider the pigeonhole statement for this particular question, The possible scores ranges from 0 to 100, which means there are 101 uniquely possible scores, that is 0 to 100. So these 101 scores act as our pigeonholes. Next, in this problems, the pigeons are 101 students who took each exam. So each student's score is an item that will be placed into one or more pigeonholes. So what we conclude is, using this generalized principle, we have n is equals to 101 students and m is equals to 101 possible scores. The calculation will be done as 101 slash 101, which is 1. So tells us that, 101 is divided by 101 is equals to 1, which tells us at least one score must have at least one student. In fact, since the number of students equals to the number of scores, a collision is guaranteed if all scores are not unique. Next, let's move on to the application of pigeonhole principle. So we have data compression. Ratio for perfect lossless of compression is impossible if reducing size. Some files will have to grow. 100% retention of original data and lossless compression. Every bit must be recoverable. Minimum 2 files that must expand if you compress n files into less than n files. Next, let us move on to the application, which is Ramsey theory. In this we have order in chaos, party example, and pigeonhole connection. So we'll understand how Ramsey theory is connected to pigeonhole principle. So first let us discuss about the problem. Ramsey theory explains the conditions under which the order must appear within a sufficiently large system. No matter how disordered it seems, it often describes as finding pattern in chaos. So let us take example as party. A classical illustration is the statement: at any party of 6 people, there will be always a group of 3 mutual friends or a group of 3 mutual strangers. This seemingly simple social observation has deep mathematical roots. So now we'll understand how the pigeonhole is connected to this concept. So this fascinating result and many others in Ramsey theory can be rigorously proven by skillful applying the pigeonhole principle in conjunction with concepts from graph theory. The choices between friendship and strangers act as pigeonhole for the relationship. Next, let us discuss another example, points and square. So if we consider, there are many examples of pigeonhole principle. Another example is points and square, which applies into pigeonhole principle. Next, let's discuss about the conclusion. So it is simple and yet powerful, existent without construction, it has wide-ranging applications, and key problem-solving tools are larger. So thank you. Please like, share, and subscribe.